Hello, everybody. I'm down here or over here in the little window. And welcome to week 1, video 2, neurons and the resting potential. And in this video, we're going to cover, hopefully background information for you guys, neuron structure, and then electricity. So what is voltage and current and conductance and resistance, followed by a discussion about the semi-permeable membrane and how that creates a membrane potential. And then what determines individual ions, equilibrium potentials, and finally, how does permeability and equilibrium potentials determine the overall membrane potential? Lots of words, with the word potential in there, lots of phrases with the word potential in there, and hopefully this is review, but if not, then we'll get you up to speed with this video, I hope. Or at least make it more clear to you which things you need more information and more background on. So these videos hopefully will get a little smoother as I go, but it's gonna start off a little rough, and I'm just gonna roll with it because in class I would roll with it, and so in video I'm gonna roll with it too, rather than spending lots of hours editing videos. So sorry if there's some rough patches, but we'll do our best. Okay, so starting with neuron structure and function, this is a picture of a full neuron and then a cell body of the next neuron in the chain. As we know, the central nervous system and the peripheral nervous system communicate with each other via chains of neurons, circuits of neurons. And so we have our cell body with the nucleus here in this picture of the neuron on the left-hand side, and you can see the dendrites that are reaching out to communicate to other neurons that are preceding it in this chain, in this network or circuit. And then you have an axon that's going to send the signal from that cell body down to the presynaptic axon terminal, where it will synapse onto the next neuron called the postsynaptic neuron in this circuit. So we have dendrites that are receiving information, axons that are transmitting information, and synapses that are using neurotransmitters largely, but sometimes sometimes electrical signals in order to tell the next neuron in the chain that it has been activated. So sometimes these terms, postsynaptic and presynaptic, can be confusing because we tend to think about a neuron as like starting in the nucleus. But of course, in the dendrites, I'm going to try drawing here. The dendrites, that word there, and pointing to there, they're receiving information from some other cell, either a neuron or a sensory cell. And so it's on the receiving side of things, and so we actually call the dendrites membrane the postsynaptic membrane because it's after the synapse. And then we call the, at the axon terminal down here, we call that the presynaptic membrane because it's on the start of before the synapse. So if we look at this cell, I'm going to pause for just a moment. You can pause the video if you want on these questions so that you have time to think about it and answer it before I tell you the answer, which is what I recommend. Where on the highlighted neuron is the postsynaptic membrane located? Okay, so hopefully you recognize that the postsynaptic neuron is after the synapse. So if we can see a synapse there between two hypothetical cells, one of them that's not highlighted, and then we can see a synapse here at the other end where that neuron is communicating to the next neuron. And so post-synapse would be this one here. This one would be pre-synapse if you're talking about this cell. So hopefully that makes sense to you. It can be sometimes confusing when you hear pre and post synapse, but hopefully it'll kind of become second nature to you guys. So this is just a reminder that neurons have a lot of different types of morphologies. They vary depending on their function. A lot of times, so you have some cells that have massively branched and huge, kind of clouds of dendrites that are essentially receiving a lot of information from a lot of different cells. And then they're translating that information into an action potential out of its cell body. And so in that case, you might have a cell that looks something like that. We are oftentimes familiar with this one, this efferent neuron over here that's communicating information from the central nervous system to an effector cell, so like a motor cell or something. They tend to have a lot of dendrites, but then really long axons that travel through the peripheral nervous system and through the body to the target cell. And then you have sensory neurons on the left-hand panel that just vary in their form and function, again, depending on which system you find them in. And you don't need to memorize these. It's just more of a reminder that there are different types of neural cells, and they look different depending on what they're supposed to do. Okay, so moving into part 2, how do neurons communicate? And the fact that they use electricity and chemicals in order to send impulses and to be able to communicate really quickly. So this requires that you maintain a baseline state, and that's when we're going to talk about the resting potential, and then also be able to generate an electrical pulse, which is an action potential, and to communicate those action potentials between cells. So this is largely achieved by the movement of charged ions, and each ion species, when I say a species, I mean a type of ion like sodium or potassium or chloride, trying to go to its own equilibrium potential. So you have membrane permeability and an electrochemical gradient that slows down or speeds up that movement of the ion. And the membrane potential is basically the net result of all of the different ions that are moving up or down their equilibrium gradient. We're going to go over all of that now. So as a reminder, an electrical gradient, opposite charges attract each other and like charges repel each other. And so we have ions common in neural communication. Sodium is a big one. That's the one that generates the action potential. Potassium is common, and calcium. Those are the cations, the positive ions. Ions with a positive charge. And then you have anions, and the main one is chloride. That's an anion. Okay, so cation is an ion that has carries a positive charge, and anions that carry a negative charge. Okay, so quick review of what is voltage and current. And I'm going to use an analogy that I borrowed from the Khan Academy online because I think it's really easy to conceptualize. So we're going to start with physical energy, and that's created with gravity. And so if we draw a mountain and we imagine that there's some rock that we do work to move up to the top of the mountain, so that requires work like from your muscles or from a ski lift, whatever it is, you've used work in order to push that rock up to the top. And at the top, it has stored or potential energy. And in this case, it's going to be kinetic energy, which if you were to release this rock and allow it to move down the hill, it would roll down. And if it were to interact with things like bouncing off of other rocks or trees or whatever, then it could do work on the way down. So that's gravity. And if you have a smaller mountain, then you have a smaller amount of stored kinetic energy there, or potential there. So if we take that same analogy and we draw another mountain, and here we're going to talk about electricity. And instead of a rock, we now have an electron. And so if we do work to push that electron up a gradient, so again, we've done work here. Your cells do this when they actively pump ions against their electric gradient. Then you've moved that electron up, and now you have what's called stored, again, a stored potential. And this is now electrical energy. And if you were to allow that electron a path to move, so if this is an electron, we could say that this is going to build up a negative charge if you're pushing electrons to one side, and so thereby the other side is going to have a positive charge. And so if you allow that electron to move wherever it wants to go, it's going to move down the hill, down the electrical gradient. And you can again have it do work on its way as it bumps into things, interacts with things in the cell. So that difference right here, basically the height of the mountain, is voltage. And this is basically what we're talking about when we talk about potential. So when we talk about arresting potential, action potential, we're talking about basically this. How big is the difference in charge from one side of a cell membrane to the other? Okay, so I just gave a clue, I guess, or intro to what I want to just refer to next, and that's this idea of a cell membrane and how it can generate a voltage difference by being a resistor, essentially. So we have two words, resistance and capacitance. And these are basically reciprocals of each other. So resistance, as the word is commonly defined, are basically factors that slow down current. Let's see, hang on. Factors that slow current. So I didn't mention that as that electron rolls down the mountain, moves from negative to positive, the actual movement, the physical movement of that electrical charge along that pathway is what current is. And capacitance are factors that that speed current. This is not really a technical definition because anyway. Okay, so if we think about our semi-permeable membrane, this is our bilipid cell membrane. And this cell membrane is a really great resistor to ions, to charged ions. Hopefully, the bilipid nature of the membrane makes it clear why, but essentially a charged ion is highly, highly hydrophilic. It really likes water. And when you have a cell, an intracellular environment that's mostly water and an extracellular environment that's mostly water, those ions are going to really not want to be in the middle of a lipid hydrophobic space inside the cell membrane. So that keeps ions on either side of the cell membrane. So it has really high resistance normally. And so you can get what we see inside cells is we have kind of big proteins that are negatively charged throughout. And then you might have, some positive ions inside. Potassium tends to be higher at rest on the inside. But then you get these big buildups of positively charged cations like sodium. wanting to come into to the negative environment of the cell, of the inside of the cell, wanting to, they're attracted to those big negative anion proteins. And so, but they can't go, right? Because they have no path. And so there's a lot of resistance there. But if you open a channel, a sodium channel, that's inside the membrane, but normally has a gate that closes it. If you open that up, then that allows sodium to travel inside the cell and start to affect the membrane potential. As positive ions move in, the membrane potential is going to go up. And so if you have a few of these, so these are, in this example is the sodium channel. Calcium channel would do the same thing. But essentially, if you allow a channel, as you open channels, you increase what's called the permeability of the cell membrane to that ion species. So whichever way it moves is going to be dependent upon its electrical and its chemical gradient. But if you open the channel, you increase permeability. And this is going to function to increase conductance across the membrane and decrease its resistance. Okay, so channels, ion channels are required for significant permeability. And the more channels you open, the more permeability you have to that ion species. Okay, so electrical gradient, you have repelling like, and opposite charges attracting to each other. You have a concentration gradient. It's coming up weird there, lesser to greater. So in other words, if you have a permeable membrane and you start on the left-hand side there with a high concentration on the left and a low concentration on the right, then if you have permeability, that ion is going to move until that concentration gradient is balanced. That's certainly going to be a review for you guys. So when we think about the cell membrane then, the membrane potential is simply the difference in voltage between the inside and the outside of the cell. So if you take a microelectrode and you place one inside the cell and one outside of the cell, then what you measure is that difference in the mountain height, right? Is it, if you have a big difference in the electrical charges on the inside and the outside, then you have a tall mountain, and vice versa. Okay, so the ionic basis of the resting potential is where we're going to go to next. And so we need to talk about two types of potentials. We have the equilibrium potential, and that's the balance point for an individual ion species. So if the membrane potential equals the individual ion's equilibrium potential, that means that there will be no movement of that ion. It means that you have satisfied the chemical electrical gradient for that ion. The membrane potential depends on all of the different equilibrium potentials for any of the ions that have permeability across the membrane. Again, we're about to go over all of this. So to illustrate the equilibrium potential, here's a cell. So the dashed line in the middle there is the semi-permeable membrane. And those big green proteins are negatively charged. Again, these are not able to move across the membrane. And at rest, if you're thinking about potassium in this example, K+, then what we see is we see a lot of potassium inside the cell and not as much potassium outside of the cell. And the cell, again, it does work to maintain that concentration gradient. And it is equivalent to pushing a rock up the mountain because the inside of the cell is negatively charged. So if you want to hold potassium inside the cell, outside of the cell, then you're going to have to limit its permeability. So there exists some membrane potential at which an ion will move equally in both directions. And essentially when you reach that membrane potential, that charge difference, then both the concentration gradient and the electrical gradient are pulling equally in opposite directions. So if we look at our example here on the screen, let's see if I can draw one here. We have essentially a potassium, because the cell does work, it spends ATP to keep potassium at a high concentration inside the cell. So that's on this side. Here's the inside of the cell. Then we have a situation where we have more potassium on the inside of the cell relative to the outside of the cell. So its concentration gradient here is pushing potassium out. If you didn't think about electrical differences at all and only thought about concentration gradients, then potassium wants to move outside of the cell. But because of these big green negatively charged proteins, the electrical gradient is attracting potassium back into the cell. So you have opposing forces here. You have concentration gradient that wants potassium to leave, but the electrical gradient that wants potassium to stay. If you open all of the channels for potassium and allowed only potassium to move across that membrane, then potassium would move equivalently in both directions when the charge difference was negative 90 millivolts. So if you make the inside of the cell 90 millivolts less than the outside of the cell, then you'll essentially be attracting, you have a strong enough electrical attraction to pull potassium opposite of its concentration gradient at the same rate. So you'll get the same amount of movement coming in down the electrical gradient as you have going out down the concentration gradient. Okay, so that's equilibrium potential for potassium. The equilibrium potential is different for each ion, and that's largely because concentration gradients are different and whether or not they're more concentrated on the inside or the outside of the cell. So in this question, we have now the inside of the cell is on the right, notice, of the cell membrane, and the extracellular environment's on the left. And in the picture, you can see the negatively charged intracellular environment that attracts sodium into the cell. But the cell does work to maintain higher sodium outside of the cell relative to the inside of the cell. So take a minute, push pause, and think about which direction are the electrical and the chemical gradients for sodium. I'll give you a second to push pause. Okay, so hopefully you thought about those things. So we'll start with the chemical gradient. So we have more sodium molecules outside of the cell than inside. So the concentration gradient is going to push sodium inside the cell. And if we think about the electrical gradient, sodium is a cation, it's positively charged, and we know that the inside of the cell is negatively charged because of those big anion proteins, or big negatively charged proteins. So the electrical gradient is also pushing sodium into the cell. So both are going in. Okay, the answer is B there. When the electrical and the chemical gradients pull in the same direction, that means there's going to be a really large driving force. And what that just means is how strong is the ion going to move? And when those two gradients are favoring movement in the same direction, you're going to have a really big driving force. But of course, that depends on what the electrical gradient is like inside the cell. And we know that the membrane potential can and does change depending on what's going on in the neuron. So essentially, the further the membrane potential is from the equilibrium potential of the ion species, the larger the driving force. So for sodium, the electrochemical gradient favors movement into the cell until the cell reaches a membrane potential of 55 millivolts. So that's essentially happens during an action potential. You get open sodium channels, the membrane potential goes up And as it becomes more and more positive, that's going to attract less and less sodium in because the electrical gradient is changing. In contrast, for potassium, the electrical chemical gradient favors movement out of the cell until the cell reaches -90. So at -90, again, as we talked about before, that's where the electrical gradient is opposing the movement due to the concentration gradient. So if we look at our question here, if a cell is at rest, and many cells, don't say most, but many cells have a resting membrane potential of -68 millivolts, then which ion has the largest driving force? Okay, so hopefully you came up with A, sodium. So you're much further from 55 millivolts than you are from -90. So sodium is going to have the biggest driving force. It's going to move the most if there's permeability to move across the membrane. Okay, so if each ion would drive the membrane potential towards its own equilibrium, then what determines the membrane potential? In other words, who wins? Which ion wins? And so this is dependent on permeability, as we've been kind of referring to frequently. So charged ions can't pass the cell membrane, and so they can't influence the membrane potential unless the gates are open and allow them to move and generate a current and change the membrane potential. So if the permeability were high for a particular ion, then the membrane potential would approach that ion's equilibrium potential. And this is described by the Nernst equation. So the Nernst equation just says that the equilibrium potential for a particular ion is due to, or will be equal to, a series of constants, which is this term here. Z refers to the charge, the valence of the ion, and then the concentration of that ion inside of the cell and outside of the cell. That'll determine the equilibrium potential. But if the membrane is permeable for 2 or more ions, so not just one, then the actual membrane potential depends on the equilibrium potential for each of the ion species and the permeability of the membrane for those ions. And essentially the ion with the greater permeability wins that battle. It pushes the cell membrane potential closer to its own equilibrium. But it's going to be some balance like tug of war is. Okay, so we have our average resting potential somewhere between -65 to -70. And if you look at this table, you can see that equilibrium potentials for each of these major ions that move in a neuron. So you have potassium's is -90, sodium's is +60, and chloride's is -63. So your average resting potential is -65 to -70. So again, a few questions, drive it home. Which ion species has the highest driving force when the cell's at rest? Pause for a moment. Okay, that should be sodium. Again, you're furthest from its equilibrium potential when you're at rest. So sodium has the highest driving force to move. So another question, does sodium or does potassium current contribute more to the resting membrane potential? In other words, given that the cell rests at say 68 millivolts, which ion must have the highest permeability when the cell is at rest? Okay, so hopefully for that one, you came up with potassium. And the clue there is that the membrane potential, the resting membrane potential, is closest to potassium, given those options. It's also very close to chloride. So theoretically, chloride could be the ion that is kind of most important for determining the resting potential. and have the highest permeability. In this, I just gave you two answers there because it turns out that chloride is really, or sorry, potassium is really the main driver of the resting potential. So I just want to show you this basically. So we've got on the y-axis here, we've got a y-axis that shows the membrane potential. And then each of the different ion species are listed there in a different color. And their equilibrium potentials are just noted on this y-axis. So you have the equilibrium potential for calcium is very high. Equilibrium potential for sodium is also quite high in the plus 55 millivolt region. And then potassium down there at -90 and chloride kind of right near rest at -64. So one hint that I want to give when you're thinking about which ion must be moving in order to generate a given membrane potential is that if the membrane potential is becoming more positive, if it's increasing, then that means that the permeability must be higher for sodium or calcium. In order to drive the membrane potential more positive, it has to be through one of those two ions. At least if you're not using cellular work to change it. And so in that case, then your permeability for sodium would be higher than the permeability for potassium. That's what happens when we think about an action potential. The sodium channels open, that increases the permeability for sodium, and so VM starts to go up. If the cell is becoming more negative, then the permeability for potassium or chloride must be higher, because those are the two ion species that have very negative equilibrium potentials. In other words, they're the two ion species that could pull the VM down if you opened up the chloride or the potassium channels. So the GHK equation is basically the Nernst equation, but for all of the ion species together. So you still have the membrane potential over here on the left. You have your constant, the same constant that was in the Nernst equation. But now you have all of the ion species that move commonly in a neuron. So you have potassium, sodium, and chloride. And you have their concentration differences. Again, that's the same as the Nernst. So that's determining the concentration gradient. But then you have the P terms for each of the ions, and that's the permeability. In other words, how many channels are open and how free is potassium or sodium or chloride able to move across the membrane and try to reach its equilibrium potential. So if you have tons of potassium channels open, you have really high permeability, and so potassium is going to determine the VM for the most part. If you have really high sodium permeability, then sodium is going to determine the VM, and you're going to see the VM start to go up. One thing I'll note is that the concentration ratio of in versus out is opposite for chloride. Hopefully that's kind of intuitive in the sense that chloride is an anion, so it's negatively charged. And so when it moves in a particular direction, it has the opposite influence on the membrane potential than the cations like potassium and sodium. So it's flipped because of its negative charge. Okay, so the membrane potential is always determined by the relative permeability of the membrane to potassium and sodium. In other words, which one of those ions is going to drive the membrane potential is dependent on how many of its channels are open. And at rest, the relative permeability is higher for potassium than it is for sodium. So the resting potential is closest to the equilibrium potential of potassium. So given that, why is the membrane potential at rest not exactly potassium's equilibrium potential? In other words, why is it -68 and not -90? Give you a second to think about that. And so the answer to that is essentially because sodium must have at least some permeability. That's the only way it can become more positive, is for sodium, potentially chloride, but again, we're thinking about cations here. For sodium to have some permeability, it can pull it a little more positive than the equilibrium potential for potassium. And this is because there are leaky sodium channels that allow some sodium to move into the cell, but not as much sodium can move as potassium. And so then you end up at -68. Okay, so that's the end of this video, and we're going to pick up on the next one, thinking about action potentials.